So we're busy looking at the basis of a real vector space. So here's three vectors. The sub S is a subset of R3. So my question is, do those vectors form a basis for R3? Now there's a lot of work that happens before this. So I'm going to skip some steps because we've been through it already. To check that this set S forms a basis for R3, I need to check two things. Firstly, that S spans R3. And secondly, that S is linearly independent. Now you need to know how to test for those three, and you need to do that for this set. To check that it spans R3 and linearly independent. You can do that on your own. I'm going to skip a couple of steps because you can't just jump here. You need to know what comes before that. But what we're going to look at is the determinant of a coefficient matrix 1, 1, 1, 2, 0, 1, and 1, minus 1, 1. We're going to look at this determinant of this coefficient matrix. And we get the coefficient matrix from a system of linear equations that gets set up with those two tests. So you need to know how to do those two tests. That determinant, once I find it, I need to see if it's non-zero. Now, yet again, something you should be able to do at this point is to calculate the determinant of a matrix. And you will find, you can do that now, you will find this determinant is equal to minus 2. So we know it's non-zero. If this determinant is non-zero, then I can speak about the solution to the systems of linear equations, which I haven't written out here, but you get that from the definitions of span and linear independence. So I know the system has a unique solution and the homogeneous system has only the trivial solution. So I can say that this set forms a basis for R3 because it spans R3 and is linearly independent. So those are the things we are looking at. Now, if I say it forms a basis for R3, what it means then, the first important thing, is that any element of R3 must be able to be written as a linear combination of those. I must be able to do it. Now, how do I do that? Sometimes it's obvious, but the numbers aren't always that nice. So how do I get to be looking at a linear combination of V1, V2, V3? So what do I want? Well, I want to find a K1, K2, and K3 such that K1 times V1, which is 1, 2, 1, plus K2 times V2, which is 1, 0, minus 1. Let me actually write this below. K1 times 1, 2, 1, plus K2 times 1, 0, minus 1, plus K3 times 1, 1, 1. That linear combination must give me 7, 4, 2. Now, I know S forms a basis, so there has to be a solution to the system. The system has to have a solution. There's no way around it. All right, so thankfully I know that I can find them. I should be able to find them. Now we're just going to look at the process. So if I write this vector equation as a system, I get 1k1 plus 1k2 plus 1k3 is equal to 7. If I look at the second entry, 2k1 plus 0k2 plus k3 gives me 4. And the third entry is k1 minus k2 plus k3 must give me 2. So if we look at the augmented coefficient matrix, because I want to solve for k1, 2, and 3. 1, 1, 1, 2, 0, 1, 1, minus 1, 1. If I look at that coefficient matrix, and if you haven't picked up on it yet, the coefficient matrix, the columns is just the vectors v1, v2, and v3. But if I look at the coefficient matrix, let's find the augmented coefficient matrix, 7, 4, 2. If I look at the augmented coefficient matrix, I can use Gaussian elimination to solve it. You can also use the inverse matrix method, or you can use Cramer's rule, because the system has a unique solution, so you can use any three of those methods. I'm just going to use Gaussian elimination, but I'm not going to show the steps. You should know the steps, so you can go through the steps and make sure you can get there. But what this should reveal is 1, 0, 0, minus a half, 0, 1, 0, 5 over 2, 0, 0, 1, 5. So this system should reduce to that. So what that means is K1 is minus a half, K2 is 5 over 2, and K3 is 5. Now, what does that mean? That means that if I take minus a half times 1, 2, 1, plus 5 over 2 times vector 2, which is 1, 0, minus 1, plus 5 times 1, 1, 1, I should get this vector B. Well, let's see. Minus a half plus 5 over 2 is 2 plus 5. That gives me 7. So far, so good. Minus 1 plus 0 plus 5 gives me 4. And minus a half minus 5 over 2, that gives me minus 6 over 2. So it's minus 3 plus 5 gives me 2. So there we go. We have shown how to write B as a linear combination of elements of S. And that's what we want because S forms a basis for R3. So any vector in R3. Now I'm using whole numbers here. You can use the ugliest numbers you want. Any subset element of R3 must be able to be written as a linear combinations of those elements of the basis. All right. Now, not only can they be written, this VB be written as such, but it's a unique representation. There's no other K1, K2, and K3 that can get me there. It's a one unique solution. And that comes from the fact that the system has a unique solution. There's no other solution to this system. All right, so we can generalize that concept. All right, so these next concept we're looking at is that of dimension. So firstly, we say a vector space is finite dimensional if the basis for that vector space has a finite number of elements. So we see the basis of R3 has 3 elements. Basis for Rn has n elements. Basis for Pn has n plus 1 elements. The basis for M22 has 1, 2, 3, 4 elements. So what that means is these are all finite dimensional vector spaces. Now, added to that, if I've got a finite dimensional vector space, then any 2 bases for that vector space have the same number of elements. And that's quite a powerful statement. Any 2 bases for a vector space. So we've now looked at bases for R3 and R2. We've generated a couple, but every basis for R2 has only 2 elements. Every basis for R3 has only 3 elements. And that is the dimension of a vector space, the number of elements in the basis. So if I've got R3, the dimension is 3. Rn, the dimension is n. Pn, the dimension is n plus 1. Now these are some standard bases, but we've generated other bases for R3. And we saw they also have 3 elements, and so on. So the dimension of a vector space is the number of elements in the basis. All right, now, next thing. If I've got a finite dimensional vector space, and I've got a finite set of linear independent vectors, then that set can be expanded, if needed, to form a basis. So let's look back at one of our previous examples. We've shown that this set S with V1, V2, and V3 is linearly dependent. We showed that V3 is just V1 plus V2. So we've shown I can get V3 from V1 and V2. But V1 and V2 are linearly dependent. So if I've got the set S with only V1 and V2, what this theorem tells me is I can expand the set because we know a basis for R3, because this is a subset of R3, a basis for R3 needs 3 elements in. So I need another element in there if I want to expand the set. But it's very easy to do that. Now, you can do it by trial and error and keep testing, but that doesn't sound like a very algebraic way, so we're going to look at an algebraic way to get that element. So if I say, let's our new vector that we want to add there be u, let it just be equal to, let's call it xyz, some element of R3. I want u to be my third vector in S, so S can be a basis for R3. Now we already know we're looking at span and we're looking at linear independence. What that's going to generate are systems of linear equations. So we're going to be looking at the determinant of the coefficient matrix of the system, which will be 1, 1, 2, 1, 0, 1, and x, y, z. I want that determinant to be non-zero. So the question is, what must x, y, and z be for that determinant to be non-zero? All right, so let's see what this determinant is. Before we set it non-zero, let's see what this determinant is. You can use cofactor expansion along any row and column. Take time, do that, make sure you can get the determinant right, and you will get to x plus y minus z. So there's a relationship between x, y, and z. It has some similarity to the relationship we saw earlier. Now what do I want? I want x plus y minus z to not be zero. As long as that's not zero, my system will be linearly independent, my set will be linearly independent, and it will span. So my set, if I add u to it. So we just want to choose the x, y, and z, so x plus y minus z is non-zero. So you can literally generate an infinite number of, you can have 1, 1, 5, because 1 plus 1 minus 5 is non-zero. Minus 4, 2, 1. Minus 4 plus 2 minus 1 doesn't give me 0. So you can generate a whole lot for u. So let u just be any vector x, y, z such that x plus y minus z is non-zero. Then the set with v1, v2, and v3. v3, there's no v3 here. We don't want v3. v3 mess things up. The set with v1, v2, and u will form a basis for R3. So that is what we are looking at. All right, then one more theorem to look at. If V is an n-dimensional real vector space, so if I know the dimension of V, for example, R3, I know the dimension is 3, R2, I know the dimension is 2, and so on, then if I've got a set of n linearly independent vectors, it'll form a basis. So what we're saying is, if the number of elements of my set is right, so if I've got a subset, let's say S, let's look at a subset of R2, has V1 and V2, some subset of R2, and I know S is linearly independent, then I can conclude that it'll form a basis. For R2. Because there's the right number of elements in, they're linearly independent, so the span of S will be the whole of R2. So that's a very powerful function, a very powerful theorem linking the dimension and linear independence to forming a basis for R2 or for any vector space V.